On any clear night, far from the glow of city lights, the sky reveals itself as something almost impossibly vast. Thousands of stars stretch from horizon to horizon, some bright enough to catch your attention immediately, others so faint they seem to appear only when you stop trying to look directly at them. They feel permanent, they feel ancient, and in a sense, they are. Many of the stars visible to the unaided eye tonight have been shining for millions of years, some for billions. Their light has traveled across distances so enormous that the human mind struggles to hold the numbers in any meaningful way. But there is something about stars that the night sky does not easily reveal. Every one of them was born, every one of them is aging, and every one of them, without exception, will eventually die. This is not a poetic metaphor. It is a physical reality. Stars are not eternal fixtures placed permanently in the sky. They are objects governed by the same laws of physics that shape everything else in the universe: gravity, pressure, temperature, nuclear energy. They ignite, they burn, they change, and when the conditions inside them can no longer sustain the delicate balance that keeps them alive, they end. Some end quietly. Others end in explosions so powerful they briefly outshine entire galaxies. The story of how stars are born, how they live, and how they die is one of the most important stories in all of science. It is the story that explains where the chemical elements come from, why galaxies look the way they do, how planets form, and ultimately, how life itself became possible. Without the birth and death of stars, the universe would contain almost nothing except hydrogen and helium. Two elements that alone could never build a world like ours. For most of human history, stars were mysteries. Ancient civilizations watched them move across the sky and built entire mythologies around their patterns, but no one understood what they truly were. It was only in the last century and a half that science began to unravel the real nature of stars, not as points of divine light, but as enormous spheres of hot gas undergoing nuclear reactions so powerful that they sustain themselves for timescales almost beyond comprehension. Today, astrophysicists understand stellar evolution in remarkable detail. They can trace the life of a star from its first gravitational stirrings inside a cold cloud of gas and dust, through the moment fusion first ignites in its core across the long, stable years of its prime, and into the dramatic final stages that await when its fuel supply begins to fail. The story changes depending on the mass of the star. A small, modest star follows a gentle path. A massive star follows a violent one. But every star, regardless of size, follows the same fundamental arc: birth, life, transformation, and end. This is the story we are about to follow. Not the story of any single star, but the story of all of them. The processes that govern stellar evolution are universal. They operate in every galaxy, in every cluster, in every corner of the observable universe. The star nearest to Earth, our own sun, follows the same rules as a blue supergiant burning 40,000 light years away in a distant spiral arm of the Milky Way. The physics does not change, only the scale, the timeline, and the consequences differ. We will begin where every star begins, in darkness, in the cold, quiet regions of space, where vast clouds of molecular gas drift slowly through the galaxy, waiting for something to disturb them. It is there, inside these invisible nurseries, that the first seeds of new stars are planted, and it is from there that the longest and most consequential journey in the cosmos begins. The space between stars is not empty. It may appear that way from Earth, where the night sky seems to consist of bright points separated by pure darkness. But the darkness is an illusion of distance and scale. The vast regions between stellar systems are filled with material, thin, cold, and spread across enormous volumes, but undeniably present. This material is called the interstellar medium, and it is from this substance that every star in the universe has been born. The interstellar medium is composed primarily of gas and dust. The gas is overwhelmingly hydrogen, the simplest and most abundant element in the cosmos, with smaller amounts of helium and trace quantities of heavier elements. The dust consists of tiny solid particles, microscopic grains of silicates, carbon compounds, and ice, each one far smaller than a grain of sand. Individually, these particles are almost nothing, but collectively, spread across light years of space, they form structures of extraordinary scale. The most important of these structures, at least for the story of stellar birth, are molecular clouds. These are regions where the interstellar medium has gathered into denser concentrations. Clouds of cold gas and dust that can stretch across tens or even hundreds of light years. Inside a molecular cloud, temperatures drop to extraordinarily low levels, often just 10 to 20 degrees above absolute zero. At these temperatures, hydrogen atoms bond together into molecular hydrogen, which gives these clouds their name. The interior of a molecular cloud is among the coldest environments in the entire universe. They are also among the darkest. The dust within a molecular cloud is dense enough to block the light of stars behind it. When astronomers first observed these regions, they appeared as dark patches against the brighter background of the Milky Way holes in the sky, where no stars seem to exist. It took decades to understand that these were not absences of matter, but concentrations of it. The darkness was not emptiness, it was substance. Some of these molecular clouds are enormous. The Orion Molecular Cloud Complex, one of the nearest large star-forming regions to Earth, spans hundreds of light years and contains enough material to form tens of thousands of stars. Other clouds are smaller, producing only a handful of new stars over millions of years. But regardless of size, the fundamental process is the same. Somewhere inside the cloud, something disturbs the delicate balance between the outward pressure of the gas and the inward pull of gravity. And when that balance tips, even slightly, a star begins to form. The triggers for this collapse vary. Sometimes it is the shock wave from a nearby supernova, the death of one star sending a pressure wave through surrounding space that compresses a region of cloud just enough to start the process. Sometimes it is the collision between two clouds, or the gravitational influence of a passing star, or the density waves that ripple through the spiral arms of a galaxy. In some cases, the cloud may simply reach a critical density on its own through the slow accumulation of material over millions of years. The specific trigger matters less than what happens next. When a region of the cloud becomes dense enough, gravity begins to win. The gas and dust in that region start falling inward, drawn toward the center of the densest point. This process is called gravitational collapse, and once it begins, it accelerates. As material falls inward, the center becomes denser. As it becomes denser, its gravitational pull strengthens. As its pull strengthens, more material falls inward. The process feeds itself. This collapsing region is called a dense core, and it is the earliest recognizable stage of a forming star. A single molecular cloud can contain dozens or even hundreds of dense cores, each one potentially forming its own star or group of stars. The cores are small by astronomical standards, perhaps a fraction of a light year across, but they contain the mass of entire stellar systems. As the core collapses, something important happens. The material does not simply fall straight to the center, because the original cloud was not perfectly still. It had slight rotational motion. Inherited from the larger motions of the galaxy, the collapsing material begins to spin. Conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling their arms inward, ensures that as the cloud contracts, its rotation accelerates. This rotation flattens the infalling material into a disk shape with the densest concentration at the center. The object forming at the center of this disk is called a protostar. It is not yet a true star. No nuclear fusion is occurring in its interior. It is simply a growing ball of gas and dust, heated by the energy of gravitational contraction. As material continues to rain down onto the protostar from the surrounding disk, its temperature rises, its pressure increases. It begins to glow, not from nuclear reactions, but from the sheer energy of compression. This phase can last for hundreds of thousands of years. During this time, the protostar is deeply embedded within its natal cloud. Invisible to optical telescopes, it can only be observed in infrared and radio wavelengths, where the heat of the forming star manages to penetrate the surrounding dust. Much of what astronomers know about this stage comes from infrared observatories like the Spitzer Space Telescope and the Herschel Space Observatory, which were designed specifically to peer through dust and reveal the hidden processes of star formation. The disk surrounding the protostar, known as a protoplanetary disk or circumstellar disk, plays a crucial role. It is the reservoir from which the protostar continues to grow, and it is also the environment where planets will eventually form. The same disk that feeds a growing star also plants the seeds for future worlds. This connection between star formation and planet formation is one of the most profound in all of astrophysics. It means that the birth of a star is, almost always, also the birth of a planetary system. As the protostar continues to accumulate mass, its core temperature steadily rises. Gravitational energy converts into thermal energy with relentless efficiency. The interior grows hotter, denser, and more pressurized with each passing century. Eventually, after perhaps a few 100,000 years of contraction, the core temperature reaches a critical threshold, approximately 10 million degrees. At this temperature, something extraordinary happens. The hydrogen nuclei in the core protons, stripped of their electrons by the extreme heat, begin moving fast enough to overcome their mutual electrical repulsion. They collide with sufficient energy to fuse together, forming helium nuclei and releasing enormous amounts of energy in the process. This is nuclear fusion, and ignition marks the true birth of a star. The moment is not dramatic in the way one might expect. There is no explosion, no sudden flash visible from the outside. The onset of fusion is gradual, building over time as more and more of the core reaches the necessary temperature. But once hydrogen fusion is fully established, a new equilibrium takes hold. The energy released by fusion creates an outward pressure, radiation pressure and thermal pressure, that balances the inward pull of gravity. The star stops contracting. It stabilizes. It finds its balance. This balance between the inward force of gravity trying to crush the star and the outward pressure of fusion energy trying to blow it apart is called hydrostatic equilibrium. It is the defining condition of a stable star. As long as this balance holds, the star will continue to shine. It will burn steadily, converting hydrogen into helium in its core, releasing energy that travels outward through the star's interior and eventually radiates into space as light and heat. The newborn star has arrived on what astronomers call the main sequence, the long, stable phase of stellar life, where a star spends the vast majority of its existence. For a star like our Sun, this phase will last approximately 10 billion years. For a star much smaller than the Sun, it may last trillions of years, far longer than the current age of the universe. For a star much more massive, it may last only a few million years, a brief, brilliant flash by cosmic standards. But regardless of how long the main sequence phase lasts, the fundamental process remains the same. Gravity pulls inward, fusion pushes outward, and the star exists in the space between these two forces, shining steadily into the cosmos, converting the simplest element in the universe into something heavier, and releasing the energy that lights up galaxies. The molecular cloud, once cold and dark and silent, has given birth to light. The main sequence is not a place. It is not a location in space or a physical destination that a star travels toward. It is a condition, a state of being defined by a single, elegant balance. As long as a star fuses hydrogen into helium in its core, and as long as the energy produced by that fusion is sufficient to resist the inward crush of gravity, the star remains on the main sequence. It remains stable. It remains alive. For most stars, this is the longest phase of existence by an enormous margin. Our Sun, a fairly ordinary main sequence star, has been fusing hydrogen in its core for approximately 4.5 billion years, and it will continue doing so for roughly another 5 billion. That means the Sun will spend approximately 10 billion years in this single phase of its life, a duration so vast that it dwarfs every other stage of stellar evolution combined. The Sun's birth took a few 100,000 years. Its death will unfold over perhaps 1 billion years, but its main sequence life spans 10 billion. The stable, quiet middle of a star's existence is by far the dominant chapter of the story. What happens during those billions of years is, on the surface, deceptively simple. Deep in the core, where temperatures exceed 15 million degrees and pressures are crushing beyond any human experience, hydrogen nuclei collide and fuse. The dominant process in stars like the Sun is called the proton-proton chain. In this reaction, 4 hydrogen nuclei, 4 individual protons, are gradually fused together through a series of intermediate steps to produce 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and a release of energy. The energy emerges primarily as gamma-ray photons, which begin a long journey outward through the star's interior. That journey is remarkably slow. A photon produced in the core of the Sun does not travel directly to the surface. Instead, it is absorbed and re-emitted countless times by the dense plasma surrounding it, bouncing in random directions through a region called the radiative zone. The photon's path is so tortuous, so filled with collisions and redirections, that it takes an estimated 100,000 to 200,000 years for the energy generated in the core to reach the outer layers of the star. By the time that energy finally arrives at the surface and radiates into space as visible light, the fusion reaction that created it occurred long before recorded human history. Above the radiative zone, in stars like the Sun, lies the convective zone. Here, the mechanism of energy transport changes. Instead of radiation bouncing from particle to particle, the energy is carried by the physical movement of hot gas rising toward the surface, cooling, and sinking back down, a process called convection. These convective currents create a churning, dynamic layer beneath the star's visible surface, driving patterns that can be observed as granulation, a constantly shifting mosaic of bright cells and darker boundaries visible on the Sun's photosphere through specialized telescopes. The surface itself, the photosphere, is where the star's energy finally escapes into space. For the Sun, the photosphere has a temperature of roughly 500 degrees Celsius, hot enough to glow with a familiar warm, yellow-white light that illuminates our world. But this temperature is specific to the Sun. Other stars have very different surface temperatures, and those differences produce very different colors. This is where mass becomes the most important variable in stellar evolution. The mass of a star at birth determines nearly everything about its future: how hot it will burn, what color it will shine, how long it will live, and how it will eventually die. Mass is destiny for a star, and the range of possible stellar masses produces an extraordinary range of stellar lives. The smallest stars that sustain hydrogen fusion are called red dwarfs. These are stars with masses, roughly, between 8% and 50% of the Sun's mass. They are by far the most common type of star in the universe. Astronomers estimate that red dwarfs account for approximately 70 to 80% of all stars in the Milky Way. Yet they are so dim that not a single red dwarf is visible to the unaided eye from Earth. Every star you have ever seen in the night sky is brighter, hotter, and more massive than a red dwarf. red dwarfs burn their hydrogen fuel with extraordinary efficiency and extraordinary patience. Because their cores are smaller and less pressurized than those of larger stars, the rate of nuclear fusion is much lower. They produce far less energy per second, which means they consume their fuel far more slowly. The result is a lifespan almost beyond comprehension. A red dwarf with half the Sun's mass might remain on the main sequence for 80 billion years or more. The smallest red dwarfs, barely above the minimum mass required for sustained fusion, could potentially burn for trillions of years timescales so long that not a single red dwarf in the history of the universe has yet had time to die of old age. Every red dwarf ever born is still shining today. These small stars are also fully convective, meaning that the churning convective currents extend all the way from the surface to the core. This has a profound consequence. In a star like the Sun, only the hydrogen in the core is available for fusion. The hydrogen in the outer layers never reaches the center and never participates in nuclear reactions. But in a fully convective red dwarf, material from the outer layers is continuously cycled down to the core and mixed with the fuel supply. The entire star participates in fusion over its lifetime. Nothing is wasted. This is why red dwarfs last so extraordinarily long. They use nearly all of their hydrogen, not just the fraction trapped in the core. At the opposite extreme are the most massive stars in the universe, blue giants and blue supergiants with masses 10, 20, 50, or even more than 100 times the mass of the Sun. These are the rarest stars in any galaxy, but they are also the most luminous, the most dramatic, and the most consequential. A massive star burns its hydrogen fuel at a furious rate. The core of a star, 50 times the Sun's mass, is so hot and so dense that fusion reactions proceed at a pace millions of times faster than in the Sun. The star produces an astonishing amount of energy. A blue supergiant can outshine the Sun by a factor of several 100,000 or even 1,000,000. But this brilliance comes at a cost. The fuel supply, though enormous by most standards, is consumed so rapidly that the star's main sequence lifetime is measured not in billions of years, but in millions. A star of 50 solar masses might exhaust its core hydrogen in just 3 to 4 million years. By comparison, our Sun will have been burning for 10 billion years when it finally runs out of fuel. Massive stars live fast and die young. The relationship between mass and lifetime is one of the most fundamental in stellar astrophysics. It is not linear, it is dramatically non-linear. A star twice the mass of the Sun does not live half as long. It lives roughly 1/8 as long, because the rate of fusion increases far more steeply than the increase in available fuel. This relationship means that the universe contains an extraordinary diversity of stellar lifespans, from trillions of years for the smallest red dwarfs to mere millions for the largest blue supergiants. Between these extremes lie stars of intermediate mass, yellow stars like our Sun, slightly cooler orange stars, slightly hotter white and blue-white stars. Each occupies its own position on the main sequence, determined entirely by its birth mass. Astronomers visualize this relationship using a tool called the Hertzsprung-Russell diagram, named after the two astronomers who independently developed it in the early 20th century. The diagram plots stars according to their luminosity and surface temperature, and when a large number of stars are plotted together, a clear pattern emerges. Main sequence stars form a continuous band running from hot, luminous blue stars in the upper left to cool, dim red stars in the lower right. The Sun sits comfortably in the middle of this band, a modest medium temperature, medium luminosity star that is neither remarkable nor insignificant. The Hertzsprung-Russell diagram is more than a classification tool. It is a map of stellar evolution. A star's position on the diagram tells astronomers not only what the star looks like today, but what it will become in the future. when a star eventually exhausts the hydrogen in its core, it will leave the main sequence and move to a different region of the diagram, a transition that signals the beginning of the end. But for now, during the long main sequence phase, the star simply shines. It converts hydrogen into helium, releases energy, and maintains its hydrostatic equilibrium with extraordinary precision. The balance is self-correcting. If the rate of fusion increases slightly, the star expands a little, which lowers the core temperature and pressure, which slows fusion back down. If fusion decreases slightly, the star contracts a little, which raises core temperature and pressure, which increases fusion again. This feedback loop keeps the star remarkably stable over immense timescales. During these quiet billions of years, the star is not entirely unchanging. It evolves slowly. As hydrogen is converted to helium in the core composition gradually shifts. The growing helium content changes the core's opacity and mean molecular weight, which subtly alters the rate of energy production. Over billions of years, a star like the Sun gradually brightens. The Sun today is roughly 30% more luminous than it was when it first arrived on the main sequence 4.5 billion years ago. This slow brightening will continue for the remainder of the Sun's main sequence life, with significant implications for the future habitability of Earth. But these changes are imperceptibly gradual on any human timescale. From one century to the next, from one millennium to the next, the Sun appears constant. The stars in the night sky appear fixed. The universe appears still. It is only when we stretch our perspective across millions and billions of years that the true nature of stars becomes visible, that they are not permanent, not unchanging, not eternal. They are processes unfolding on timescales that dwarf everything in human experience, but are finite nonetheless. And eventually, inevitably, the fuel runs out. For billions of years, the balance holds. Gravity pulls inward. Fusion pushes outward. The star shines with steady, patient brilliance, converting hydrogen into helium deep within its core, releasing the energy that sustains everything. From the outside, nothing appears to change, but inside, something has been quietly building a transformation so gradual that it would be undetectable across any span of human observation, yet so inevitable that no star in the universe can avoid it. The core is running out of hydrogen. This does not happen suddenly. There is no moment when the fuel gauge drops to zero and the star abruptly stops. Instead, the transition is slow, spanning millions of years even for massive stars, and hundreds of millions for smaller ones. As fusion converts hydrogen into helium, the core gradually becomes richer in helium and poorer in hydrogen. The hydrogen that remains is increasingly diluted, mixed into a growing mass of helium ash that cannot participate in the proton-proton chain or the CNO cycle. The fuel is still there, but there is less of it with each passing era, and the helium accumulating at the center has no way to burn, not yet. The core is not hot enough, not dense enough to ignite helium fusion, and so the helium simply sits there, inert, growing heavier, growing denser, waiting. This is the beginning of the end of a star's main sequence life. Not a dramatic catastrophe, but a quiet shift in chemistry that alters everything. As the hydrogen fraction in the core decreases, the rate of energy production begins to falter. With less fuel available per unit volume, the core generates slightly less energy per second, and because it is this energy that has been holding inward pull of gravity, a reduction in energy output means a reduction in outward pressure. The balance that has been maintained for billions of years begins to tilt. Gravity gains a small advantage. The core begins to contract. This contraction is not a collapse. It is gradual, steady, and self-reinforcing. As the core contracts, it grows denser. As it grows denser, the remaining hydrogen in the core and the hydrogen in a thin shell immediately surrounding the core is compressed to higher temperatures and pressures. And here, something remarkable happens. The increased temperature and pressure in this hydrogen shell actually accelerate fusion, producing more energy than the core was generating during the stable main sequence phase. The star does not dim, it brightens. But the energy being produced in the hydrogen-burning shell behaves differently than core fusion energy did during the main sequence. The energy output is greater, and it pours into the layers above the shell with increasing intensity. These outer layers, which had been in equilibrium for billions of years, now receive more energy than they can comfortably radiate away. They begin to expand. The expansion is extraordinary. Over the course of hundreds of millions of years for a sun-like star, the outer envelope swells to many times its original size. A star that was once roughly the diameter of our sun, about 1.4 million kilometers, across gradually inflates to a diameter tens or even hundreds of times larger. As the outer layers expand, they cool. The surface temperature drops from thousands of degrees to perhaps 3,000 or 4,000 degrees. The color shifts from yellow-white to deep orange, then to red. The star has left the main sequence. It has become a red giant. The transformation is one of the most visually dramatic in all of stellar evolution. A star that once resembled our sun, modest, stable, yellow, becomes a bloated, luminous red sphere that would, if placed where our sun is now, engulf the orbits of Mercury and Venus and possibly reach as far as Earth. The surface of the red giant is cooler than the surface of the main sequence star it once was. But because the star is so enormously larger, its total luminosity, the total amount of energy it radiates, is far greater. A red giant version of the sun would be thousands of times more luminous than the sun is today. Meanwhile, deep inside the red giant, the core continues to contract. The helium ash that has been accumulating for billions of years is now being compressed by gravity into an increasingly dense, increasingly hot ball. The core of a red giant is a strange object, a sphere of nearly pure helium compressed to densities far greater than anything found in the main sequence star it used to be. In stars below a certain mass threshold, roughly 2 solar masses, this helium core takes on unusual physical properties. The electrons within the core become degenerate, meaning they are packed so tightly that quantum mechanical effects, specifically the Pauli exclusion principle, begin to dominate their behavior. The core becomes supported not by thermal pressure, the way a normal gas would be, but by electron degeneracy, pressure, a quantum mechanical force that resists further compression, regardless of temperature. This has a critical consequence. In a normal gas, an increase in temperature causes an increase in pressure, which causes the gas to expand, which cools the gas back down. This is a natural thermostat, but in degenerate matter, pressure and temperature are decoupled. An increase in temperature does not cause an increase in pressure. The core does not expand. It does not cool itself. The temperature simply continues to rise. The core grows hotter and hotter as gravitational contraction converts potential energy into thermal energy. The hydrogen shell above it continues to burn fiercely, adding more helium ash to the growing core mass. And then, when the core temperature reaches approximately 100 million degrees, roughly 10 times the temperature required for hydrogen fusion, something sudden happens. Helium ignites. At 100 million degrees, helium nuclei finally have enough kinetic energy to overcome their mutual electrical repulsion and fuse together, the primary. Reaction is called the triple alpha process because it involves 3 helium-4 nuclei, also known as alpha particles, combining to form a single carbon-12 nucleus. The reaction is extraordinarily sensitive to temperature. A small increase in temperature produces a dramatically larger increase in the fusion rate. And because the core is degenerate, the normal thermostat does not work. When helium fusion begins and releases energy, the temperature rises, but the degenerate core does not expand. It does not cool. The rising temperature accelerates the fusion rate, which releases more energy, which raises the temperature further, which accelerates the fusion rate again. The result is a thermonuclear runaway, a violent, explosive event that occurs deep inside the core of the red giant. This event is called the helium flash. The helium flash is astonishingly powerful. In the space of seconds to minutes, the energy released in the core rivals the luminosity of an entire galaxy, roughly 10 billion times the sun's normal energy output. Yet, despite this extraordinary violence, the helium flash is invisible from the outside. The enormous energy released is entirely absorbed by the overlying layers of the star. It does not reach the surface. It does not produce a visible explosion. The outer layers of the red giant barely notice. The most powerful event in the star's entire life since its birth occurs in complete silence, hidden beneath trillions of tons of stellar material. What the helium flash does accomplish is the end of degeneracy in the core. The enormous energy input finally raises the core temperature, high enough to lift electron degeneracy. The core transitions back to a normal gas, expands slightly, and settles into a new equilibrium one, in which helium is now fusing steadily in the core through the triple alpha process, while hydrogen continues to burn in a shell surrounding the core. The star adjusts. Its outer layers contract somewhat. Its luminosity decreases from the peak it reached at the tip of the red giant branch. It settles onto what astronomers call the horizontal branch of the Hertzsprung. Russell diagram a new, second phase of stable burning, shorter and less luminous than the main sequence, but nonetheless a genuine period of equilibrium. The star has found a new fuel source. It has been given a second life, but this second life is far shorter than the first. Helium fusion produces far less energy per reaction than hydrogen fusion, and the star's energy demands have grown considerably. The helium core fuel supply is consumed much more rapidly than the hydrogen supply was. For a star like the Sun, the helium burning phase on the horizontal branch lasts roughly 100 million years less than 2% of the duration of its hydrogen-burning main sequence life. The clock is ticking faster now. During this phase, the triple alpha process steadily converts helium into carbon. Some of the carbon nuclei capture additional helium nuclei through a reaction that produces oxygen-16. So the core gradually transitions from helium to a mixture of carbon and oxygen, two elements that are among the most important in the universe. Carbon is the backbone of organic chemistry. Oxygen is the most abundant element in Earth's crust. Both were forged here, inside the cores of aging stars, through the patient work of helium fusion. Not every star experiences the helium flash in the same way. Stars more massive than roughly 2 solar masses reach helium ignition temperatures before their cores become degenerate. In these stars, helium ignites gently without a flash because the normal gas thermostat is still functioning. The core expands as it heats, regulating the fusion rate naturally. The result is the same helium burning on the horizontal branch, but the path to get there is less violent. For stars at the lower end of the mass range, the story is different entirely. Stars with masses below roughly half the Sun's mass, the red dwarfs we encountered earlier, will never reach helium ignition temperatures at all. Their cores will never become hot enough to fuse helium. When they eventually exhaust their hydrogen supply, trillions of years from now, they will simply contract and cool, fading slowly into darkness without ever experiencing the red giant phase, the helium flash, or any of the dramatic transformations that await more massive stars. But this endpoint is so far in the future that it remains entirely theoretical. The universe is not yet old enough for any red dwarf to have reached this stage. For stars in the intermediate range, stars like our Sun, the horizontal branch is a temporary reprieve. The helium is burning, the star has stabilized, and for a brief cosmic interval, Equilibrium has returned, but the fuel is limited. The carbon and oxygen accumulating in the core cannot be burned. The core is not hot enough, and for these intermediate mass stars, it never will be. The carbon-oxygen core grows steadily heavier, denser, and more compressed, just as the helium core once did during the late main sequence. And when the helium in the core is finally exhausted, the star faces the same crisis it faced before, but this time, there is no new fuel source waiting to ignite. The star has entered the final stages of its life. When the helium fuel in the core is finally spent, the star faces a crisis it cannot solve. The core is now composed almost entirely of carbon and oxygen, two elements that require temperatures far beyond what an intermediate mass star can achieve in order to fuse. Carbon fusion demands roughly 500 million degrees. Oxygen fusion requires even more. For a star with a mass similar to our Sun, or even several times the Sun's mass, these temperatures are simply unreachable. The core does not have enough gravitational potential energy to compress itself to such extremes. The carbon and oxygen will never ignite. They will never become fuel. And so the core simply contracts, growing denser and hotter, but never hot enough. Gravity compresses it steadily, and once again, as happened during the red giant phase, the core becomes degenerate. Electron degeneracy pressure, that quantum mechanical resistance to further compression, halts the collapse and supports the core against gravity. The carbon-oxygen core becomes an incredibly dense object, roughly the size of Earth, but containing a significant fraction of the star's original mass. A teaspoon of this material would weigh several tons. Above this inert, degenerate core, fusion continues in two thin shells. A helium-burning shell sits immediately above the core, converting helium into carbon and oxygen and adding mass to the growing core below. Above that, a hydrogen-burning shell continues to fuse hydrogen into helium, feeding the helium shell beneath it. The star now has a layered structure, an onion-like arrangement of burning shells surrounding a dead core, all wrapped inside an enormous, distended outer envelope. This phase is called the asymptotic giant branch, and it represents the final extended chapter of life for intermediate mass stars. The star swells again, even larger than it was during its first red giant phase. Its luminosity increases dramatically. Its outer layers cool further, glowing deep red. A sun-like star on the asymptotic giant branch would expand to a radius several hundred times that of the present-day Sun, large enough to reach beyond the orbit of Mars. It would be thousands of times more luminous, a vast, cool, luminous sphere of tenuous gas surrounding a tiny, incredibly dense core. The asymptotic giant branch is an unstable phase. The two burning shells do not operate smoothly. The helium-burning shell in particular is prone to violent instability. Helium shell burning is extremely temperature sensitive, and periodically, the shell experiences brief but intense episodes of runaway fusion called thermal pulses. During a thermal pulse, the helium shell ignites with sudden ferocity, producing an enormous burst of energy over a geologically brief period, perhaps a few hundred years. This energy surge drives powerful convective currents through the star's interior, dredging material from deep layers up toward the surface. Elements forged in the interior, carbon, oxygen, and heavier elements produced through slow neutron capture processes are mixed into the outer envelope and carried to the surface. These thermal pulses recur periodically, roughly every 10,000 to 100,000 years, depending on the star's mass. Each pulse dredges more processed material to the surface, progressively enriching the star's outer layers with elements that were not present when the star was born. This process, known as the third dredge up, is one of the primary mechanisms by which stars return newly forged elements to the cosmos. Carbon. Our red giants, whose surfaces are conspicuously enriched in carbon, are the direct result of this dredging process. They represent aging stars in the act of redistributing their internal chemistry to the universe. Between thermal pulses, the star also loses mass at a prodigious rate. The outer layers of an asymptotic giant branch star are only weakly bound by gravity. The surface gravity is extremely low because the envelope has expanded to such enormous size, and the radiation pressure from the luminous interior pushes outward relentlessly. The result is a strong stellar wind, a continuous outflow of gas and dust from the star's surface into surrounding space. This wind can carry away mass at rates millions of times greater than the solar wind that currently streams from our sun. Over the course of the asymptotic giant branch phase, which lasts roughly 1 million years for a sun-like star, the star may lose 30 to 50% of its through this wind alone. The mass loss is not gentle. It is not a smooth, steady evaporation. It comes in pulses and surges, often synchronized with the thermal pulses occurring deep inside. The expelled material forms shells and rings of gas and dust surrounding the star, expanding outward into space at velocities of 10 to 30 kilometers per second. These shells carry with them the processed elements dredged up from the interior carbon, nitrogen, oxygen, silicon, and traces of heavier elements produced through nuclear reactions in the burning shells. As the mass loss continues and accelerates, the outer envelope grows thinner. The star is literally shedding itself. Layer by layer, the outer atmosphere is stripped away, exposing progressively deeper and hotter regions. The effective temperature of the visible surface begins to rise, not because the remaining material is heating up, but because the removal of cooler outer layers reveals the hotter interior beneath. The star begins to shrink, not through gravitational collapse of the whole structure, but through the erosion of its own atmosphere. Eventually, the outer envelope becomes so thin that it can no longer sustain itself. The final remnants of the hydrogen-rich atmosphere are expelled in one last episode of mass loss, and the hot, dense core is exposed directly to space for the first time. The transition is relatively rapid by astronomical standards, perhaps a few thousand years from the final thermal pulses to the complete exposure of the core. What remains is one of the most visually stunning phenomena in the night sky, a planetary nebula. The term is misleading. A planetary nebula has nothing to do with planets. The name dates to the 18th century, when early astronomers observing these objects through small telescopes noted their round, disc-like appearance, vaguely reminiscent of the discs of planets like Uranus and Neptune. The name persisted long after the true nature of these objects was understood, and it remains in use today simply through historical convention. A planetary nebula is the expelled outer envelope of a dying star, illuminated by the ultraviolet radiation of the exposed core at its center. The hot core, now approaching surface temperatures of tens of thousands or even over 100,000 degrees, emits intense ultraviolet light that ionizes the surrounding gas, causing it to glow in brilliant colors. Oxygen produces characteristic green and blue-green emission. Nitrogen and hydrogen produce red. Sulfur contributes deeper reds. The result is a luminous, often symmetrical shell of glowing gas, expanding outward at tens of kilometers per second, centered on the tiny, intensely hot remnant of the star that created it. Planetary nebulae are among the most photogenic objects in astronomy. The Hubble Space Telescope has captured hundreds of them in extraordinary detail, revealing an astonishing variety of shapes and structures. Some are nearly perfect spheres. Others are elongated, bipolar, with twin lobes of gas expanding in opposite directions. Some display intricate rings within rings, the result of multiple episodes of mass loss during the thermal pulse phase. Others show complex filamentary structures, jets, and knots that suggest the influence of magnetic fields, binary companions, or rotational effects during the ejection process. The Ring Nebula in the constellation Lyra is one of the most familiar examples, a roughly circular shell of glowing gas surrounding a tiny central star, visible only through telescopes. The Helix Nebula in Aquarius is one of the closest planetary nebulae to Earth, spanning nearly half the apparent diameter of the full moon in the sky, though far too faint to see without optical aid. The Cat's Eye Nebula displays an extraordinarily complex series of concentric shells and jets that have challenged astronomers' models of nebular formation for decades. But for all their beauty, planetary nebulae are ephemeral. The expanding gas shell dissipates into the interstellar medium over a timescale of roughly 10 to 20,000 years. Within that brief window, the nebula is visible, luminous, spectacular. After that, it fades, thins, and merges with the surrounding interstellar gas, enriching it with the elements forged during the star's lifetime. The carbon, nitrogen, oxygen, and other elements carried by the nebula become part of the raw material from which future generations of stars and planets will form. This is one of the most important processes in the chemical evolution of the universe. Stars are not merely consumers of hydrogen, they are factories. Factories that take the simplest element and transform it through billions of years of nuclear processing into the heavier elements that make rocky planets, organic molecules, and life itself possible. And planetary nebulae are the delivery mechanism. They are the means by which a star returns its manufactured products to the cosmos. At the center of the expanding nebula, the exposed core continues to cool. It no longer has any source of nuclear energy. The hydrogen and helium burning shells have been extinguished, their fuel either exhausted or expelled with the envelope. What remains is a ball of carbon and oxygen supported entirely by electron degeneracy pressure, slowly radiating away its residual thermal energy into space. This object is a white dwarf, the final remnant of a low or intermediate mass star. A white dwarf is an extraordinary object. It contains roughly 50 to 70% of the original star's mass, compressed into a volume roughly the size of Earth. The density is staggering, approximately 1 million times the density of water. A sugar cube-sized piece of white dwarf material would weigh roughly a ton. The surface temperature at the moment of formation can exceed 100,000 degrees, making the white dwarf intensely luminous in ultraviolet light despite its tiny size. But without any internal energy source, the white dwarf can only cool. It radiates heat into space, growing gradually dimmer and cooler over billions of years. The cooling process is extraordinarily slow. A white dwarf formed billions of years ago would still be faintly luminous today. The oldest white dwarfs in the Milky Way, those formed from the earliest generations of stars, have cooled to surface temperatures of just a few thousand degrees, still warm enough to glow faintly. Invisible light, dim red embers in the stellar graveyard. Theoretical models suggest that given enough time, far more time than the current age of the universe, a white dwarf would eventually cool to the point of invisibility, becoming a cold, dark, inert object sometimes called a black dwarf. But the universe is only 13.8 billion years old. No white dwarf has yet had enough time to cool completely. Every white dwarf that has ever formed is still out there, still faintly glowing, still slowly surrendering the last of its thermal energy to the void. There is a limit to how massive a white dwarf can be. This limit, known as the Chandrasekhar limit, after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in the 1930s, is approximately 1.4 times the mass of the Sun. Above this mass, electron degeneracy pressure is insufficient to support the object against gravitational collapse. No white dwarf can exceed this limit and remain stable. For isolated white dwarfs, those not interacting with a companion star, this limit is never approached because the mass loss during the asymptotic giant branch phase ensures that the final remnant falls well below 1.4 solar masses. But the Chandrasekhar limit becomes critically important in binary star systems, where a white dwarf orbiting a companion star can accumulate additional material. That, however, is a story that belongs to a different stage of the narrative. For now, the white dwarf simply exists, alone, cooling, silent. The star that once shone for billions of years, that once warmed planets, that once dominated a patch of sky, has been reduced to an object smaller than Earth, slowly fading into darkness. The planetary nebula that briefly surrounded it has dispersed into the interstellar medium. The elements it carried have joined the vast reservoir of gas and dust that fills the galaxy. Somewhere, millions of years from now, those elements may find themselves inside a new molecular cloud, participating in a new gravitational collapse, becoming part of a new star, a new planetary system, perhaps a new world. The cycle continues, but for this star, the journey is over. The story so far has followed the fate of stars, like our Sun, stars of modest mass that live long, quiet lives and end as white dwarfs surrounded by the fading glow of planetary nebulae. It is a gentle ending, as stellar deaths go. The star does not explode. It does not collapse into something exotic or terrifying. It simply sheds its outer layers, exposes its core, and cools into silence over billions of years. For the majority of stars in the universe, this is the entire story. Most stars are small. Most stars die quietly. But there are other stars rarer, more massive, more luminous, for which the story does not end so gently. These are the stars that dominate the night sky, despite their scarcity. The stars whose deaths reshape the galaxies they inhabit. The stars whose final moments produce the most violent events in the observable universe. These are the massive stars, and their fate is written in a fundamentally different language. A massive star is generally defined as one with a birth mass greater than approximately 8 times the mass of the Sun. This is a rough threshold, and the exact boundary depends on chemical composition and other factors, but it represents a critical dividing line in stellar evolution. Below this mass, a star will end as a white dwarf. Above it, the star's death will be incomparably more dramatic. The main sequence life of a massive star is, in many ways, similar to that of a smaller star. Hydrogen fuses into helium in the core. Hydrostatic equilibrium is maintained. The star shines steadily, but everything happens faster. A star of 20 solar masses exhausts its core hydrogen in roughly 10 million years. A star of 50 solar masses may do so in 3 to 4 million years. These are extraordinarily brief lifetimes by stellar standards. The Sun has already been burning for 4.5 billion years and is only halfway through its main sequence. Life, a massive star, born at the same time as the Sun, would have died billions of years ago. When a massive star exhausts its core hydrogen, it follows the same initial path as a lower mass star. The core contracts, hydrogen shell burning begins, and the outer layers expand. The star becomes a supergiant, not merely a red giant, but something far larger and far more luminous. Red supergiants can have diameters exceeding 1 billion kilometers. If placed at the center of our solar system, a red supergiant like Betelgeuse would extend beyond the orbit of Jupiter. These are among the largest individual objects in the universe, but the critical difference between a massive star and an intermediate mass star becomes apparent when the core reaches helium ignition temperature. In an intermediate mass star, helium ignites through the violent helium flash because the core has become degenerate. In a massive star, the core never becomes degenerate during this transition. It is too hot, too massive, too energetic. Helium ignites smoothly, without a flash, and the star settles into helium core burning, just as it once settled into hydrogen core burning. The triple alpha process converts helium into carbon, and alpha capture onto carbon produces oxygen, just as it does in lower mass stars. The difference is what happens next. When the helium in the core of a massive star is exhausted, the core contracts again. But this time, unlike in a sun-like star, the gravitational compression is powerful enough to raise the core temperature to the threshold required for carbon fusion, roughly 500 million degrees. Carbon ignites. Carbon nuclei fuse together to produce a mixture of heavier elements, including neon, sodium, and magnesium. This is a burning stage that lower mass stars can never reach. The Sun's carbon-oxygen core will never achieve 500 million degrees, but a star of 20 solar masses reaches this temperature almost inevitably. Carbon burning in the core is a shorter phase than helium burning, which was itself shorter than hydrogen burning. The pattern is consistent and relentless. Each successive nuclear fuel burns faster than the last, because each reaction produces less energy per fusion event, while the star's energy demands continue to grow. Carbon burning in a massive star's core may last only a few thousand years. When carbon is exhausted, the core contracts yet again. The temperature rises further. Neon ignites at roughly 2 billion degrees through a process called neon photodisintegration, where high-energy photons break apart neon nuclei, and the released particles are captured by other neon nuclei to form magnesium and oxygen. Neon burning lasts perhaps a few years, a vanishingly brief phase by any standard. After neon, oxygen ignites at roughly 2 billion degrees. Oxygen nuclei fuse to produce silicon, sulfur, and phosphorus, along with other intermediate mass elements. Oxygen burning may last a year or so. The timescales are becoming almost incomprehensibly short, and then silicon ignites. At approximately 3 billion degrees, silicon nuclei undergo a complex series of reactions, not simple fusion in the way hydrogen or helium fuse, but a rapid chain of photodisintegration and capture reactions that gradually build heavier and heavier nuclei. Silicon burning does not simply produce one element, it produces a cascade of elements climbing the periodic table, from silicon through sulfur, argon, calcium, titanium, chromium, and ultimately to iron and its neighbors, nickel, cobalt, and iron group elements. This process is extraordinarily fast. Silicon burning in the core of a massive star lasts approximately 1 day. One single day, at the end of a stellar life that may have spanned 10 million years, the star has now developed a remarkable internal structure. If it could be sliced open and examined, it would resemble an onion, with concentric shells of different compositions surrounding the core. The outermost layers still contain the original hydrogen and helium from the star's birth. Beneath that lies a helium-burning shell. Deeper still, a carbon-burning shell. Then neon, then oxygen, then silicon. And at the very center, a core of iron, the final product of silicon burning. This layered structure is one of the most extraordinary configurations in nature. Each shell burns its own fuel, producing energy and ash that feeds the layer below. The star has become a multi-stage nuclear furnace, simultaneously burning 6 different fuels in 6 concentric shells, all surrounding a core that has reached the end of the nuclear road, because iron is the end of the road. Iron 56, along with its neighbor nickel 56, sits at the peak of this nuclear binding energy curve. This means that iron nuclei are the most tightly bound nuclei in nature. Fusing iron into heavier elements does not release energy, it requires energy. And breaking iron apart into lighter elements also requires energy. Iron is a nuclear dead end. It cannot be burned. It cannot provide the star with the energy it needs to support itself against gravity. For the first time in the star's entire existence, the core has no answer to gravity's relentless inward pull. Every previous crisis, the exhaustion of hydrogen, helium, carbon, neon, oxygen, silicon, was resolved by igniting a new fuel at a higher temperature. But iron offers no such escape. The core has climbed the periodic table as far as nuclear physics will allow. There is nothing left to burn. The iron core grows rapidly as silicon burning in the surrounding shell continues to deposit more iron onto it. Within hours, the core approaches and then exceeds the Chandrasekhar limit, 1.4 solar masses. At this point, electron degeneracy pressure, which has been helping support the core, is no longer sufficient. The core has become too massive, too dense, too hot. Two processes accelerate the crisis simultaneously. First, the extreme temperatures cause iron nuclei to photodisintegrate. High-energy photons break apart the iron nuclei that took millions of nuclear processing to build, shattering them back into helium nuclei and free neutrons. This process absorbs enormous amounts of energy, robbing the core of thermal pressure support. Second, the extreme densities force electrons and protons to combine through a process called electron capture, or inverse beta decay, producing neutrons and neutrinos. The electrons that had been providing degeneracy pressure are consumed. The neutrinos, which interact almost negligibly with matter, stream outward and escape, carrying away energy. Both processes, photodisintegration and electron capture, remove pressure support from the core. The result is catastrophic. The core collapses, not slowly, not gradually. The iron core of a massive star collapses at a significant fraction of the speed of light. In less than 1 second, a single heartbeat, the core that took millions of years to build compresses from a volume, roughly the size of Earth, to a sphere, roughly the size of a city. The density reaches and surpasses nuclear density, the density of an atomic nucleus, and a new form of pressure, neutron degeneracy pressure, finally halts the collapse. The collapsing material rebounds off this suddenly rigid neutron core, and a shock wave is born. This is the beginning of a core collapse supernova, one of the most energetic events in the known universe. The shock wave, born at the boundary of the collapsing core, carries an almost inconceivable amount of energy. It races outward through the infalling layers of the star at tens of thousands of kilometers per second, slamming into silicon, oxygen, neon, carbon, helium, and hydrogen, every layer of the carefully constructed stellar onion that took millions of years to build. In a matter of hours, the shock wave tears through the entire star, accelerating the outer layers to velocities sufficient to escape the gravitational pull of the remnant core. The star is blown apart. This is a supernova. The energy involved defies any meaningful comparison to human experience. In the brief span of a few seconds, the collapsing core releases approximately 3 times 10 to the 46 joules of energy, a number so large it has no intuitive meaning. To place it in some perspective, this is roughly the amount of energy the Sun will produce over its entire 10 billion year main sequence lifetime, released in a single moment. The overwhelming majority of this energy, approximately 99%, is carried away by neutrinos, the ghostly particles produced during the neutronization of the core. These neutrinos stream outward at nearly the speed of light, passing through the star's outer layers as though they were not there, carrying their energy into the depths of space. The remaining 1% of the energy is more than sufficient to destroy the star. It is this fraction that powers the shockwave, accelerates the ejected material, heats the expanding debris to millions of degrees, and produces the visible light, X-rays, gamma rays, and radio emissions that make supernovae observable across vast cosmic distances. At peak brightness, a core collapse supernova can outshine its entire host galaxy. A single dying star, for a few weeks, radiates more visible light than the combined output of hundreds of billions of stars. Supernovae in distant galaxies are routinely observed by modern telescopes, appearing as bright new points of light where no star was individually visible before. Throughout human history, several supernovae in our own galaxy have been recorded by observers who had no understanding of what they were witnessing, only that a new star had appeared in the sky where none had been before. In the year 1054, Chinese astronomers documented a guest star that appeared in the constellation we now call Taurus. It was bright enough to be visible in daylight for several weeks and remained visible to the unaided eye at night for nearly 2 years before fading from view. Today, the remnant of that explosion is known as the Crab Nebula, a rapidly expanding cloud of gas and filamentary debris, still glowing nearly 1,000 years later, powered by the spinning neutron star at its center. In 1572, the Danish astronomer Tycho Brahe observed a supernova in Cassiopeia that challenged the prevailing Aristotelian belief that the heavens were unchanging and perfect. In 1604, Johannes Kepler observed another, the last supernova visible to the unaided eye in the Milky Way. No naked eye supernova has been observed in our galaxy since. The most recently observed nearby supernova occurred in 1987. Not in the Milky Way, but in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, approximately 168,000 light-years away, designated SN 1987A. It was the closest supernova observed since the invention of the telescope and provided an unprecedented opportunity for modern astrophysics. For the first time, neutrinos from a supernova were detected. Roughly 24 neutrino events recorded by detectors in Japan and the United States, arriving approximately 3 hours before the first visible light. This confirmed the theoretical prediction that the core collapse produces a tremendous burst of neutrinos before the shockwave reaches the surface and the star becomes optically bright. SN 1987A has been studied continuously ever since, and its expanding remnant continues to reveal new details about the supernova process. The explosion itself is not merely destructive, it is also profoundly creative. The passage of the shockwave through the outer layers of the star generates temperatures and pressures high enough to drive a final burst of nuclear reactions, explosive nucleosynthesis. In these extreme conditions, elements that were never produced during the star's quiet life are forged in an instant. The shockwave compresses and heats the silicon and oxygen shells to temperatures exceeding 5 billion degrees, driving rapid nuclear reactions that produce vast quantities of radioactive nickel-56. This unstable isotope decays first to cobalt-56 and then to stable iron-56 over a period of weeks and months, and it is the energy released by this radioactive decay that powers much of the supernova's visible light in the weeks following the explosion. Without nickel-56 decay, a supernova would fade from view far more rapidly than it does, but the nucleosynthesis goes further. The intense neutron flux produced during the explosion drives a process called the R process, rapid neutron capture. In this process, atomic nuclei are bombarded with free neutrons so rapidly that they capture many neutrons before having time to undergo radioactive decay. The result is the creation of extremely heavy, neutron-rich nuclei that subsequently decay into stable heavy elements: gold, platinum, uranium, thorium, europium, and dozens of other heavy elements beyond iron on the periodic table are produced through this process. These are elements that cannot be created through any of the steady fusion processes that operate during a star's normal life. They can only be forged in the extreme conditions of a supernova explosion, or, as more recent research has shown, in the mergers of neutron stars. The expanding debris cloud, the supernova remnant, carries all of these elements outward into the interstellar medium. Over thousands of years, the remnant expands, cools, slows, and gradually merges with the surrounding gas and dust. The elements it carries, carbon, oxygen, silicon, iron, gold, uranium, and everything in between, are mixed into the interstellar medium, enriching it with the products of stellar nucleosynthesis. This enriched material becomes part of the raw material from which new molecular clouds form, new stars ignite, and new planetary systems coalesce. This process of stellar recycling is the reason the universe today is chemically different from the universe that existed shortly after the Big Bang. In the first few minutes after the Big Bang, nuclear reactions produced only hydrogen, helium, and trace amounts of lithium. Every other element in the periodic table, every atom of carbon in your body, every atom of oxygen in the air, every atom of iron in your blood, every atom of calcium in your bones was produced inside a star and released into the cosmos through stellar death. Some of these elements were gently returned to space through the stellar winds and planetary nebulae of lower mass stars. Others were violently scattered through supernova explosions. But in every case, the origin is the same. The elements that make up the Earth, the oceans, the atmosphere, and every living thing were manufactured inside stars that lived and died before our solar system existed. This realization, which emerged gradually through the 20th century, is one of the most profound in all of science. We are, in a literal and verifiable sense, made of stellar material. The atoms in a human hand may have been forged in a dozen different stars across billions of years of galactic history, scattered by supernovae, gathered into molecular clouds, incorporated into a new solar nebula, condensed into a rocky planet, and eventually assembled by biological processes into living tissue. The connection between stellar evolution and human existence is not poetic embellishment. It is physical fact. Back at the site of the explosion, what remains at the center depends on the mass of the collapsing core. For most core-collapsed supernovae, the remnant is a neutron star, an object of almost unimaginable density. A neutron star is the collapsed core of the massive star, compressed to nuclear density, with a mass typically between 1.4 and 2.0 solar masses, packed into a sphere roughly 20 kilometers in diameter. The density is approximately 1 billion tons per cubic centimeter. The surface gravity is roughly 200 billion times the surface gravity of Earth. The magnetic field can be trillions of times stronger than Earth's magnetic field. Neutron stars are supported against further gravitational collapse by neutron degeneracy pressure. The quantum mechanical resistance of neutrons to being compressed beyond nuclear density. This is the same principle applied to neutrons rather than electrons that supports white dwarfs. But neutron stars exist at a far more extreme density in a physical regime where the behavior of matter is still not entirely understood. Many neutron stars are born, spinning rapidly, a consequence of conservation of angular momentum during the core collapse. A core that was rotating slowly before collapse spins enormously faster when compressed to a fraction of its original size. Just as the protostar spun faster as it contracted from a molecular cloud, newborn neutron stars can rotate dozens or even hundreds of times per second. Combined with their intense magnetic fields, this rapid rotation produces beams of electromagnetic radiation, radio waves, X-rays, and sometimes gamma rays that sweep through space like the beam of a lighthouse. When one of these beams happens to cross Earth's line of sight, we observe it as a regular series of pulses. These objects are called pulsars, and their discovery in 1967 by Jos Bell Burnell and Anthony Hewish was one of the landmark achievements of 20th century astrophysics. The Crab Nebula pulsar SAR, spinning approximately 30 times per second at the center of the remnant from the 1054 supernova, is one of the most studied pulsars in the sky. Its rotational energy powers the nebula's continued emission nearly 1,000 years after the explosion, feeding energy into the expanding cloud through a relativistic wind of charged particles. Without the pulsar, the Crab Nebula would have faded long ago. But not every core collapse produces a neutron star. For the most massive stars, those whose cores exceed roughly 2 to 3 solar masses, even after the explosion has ejected the outer layers, neutron degeneracy pressure is insufficient. No known force can halt the collapse. The core compresses beyond nuclear density, beyond any density that current physics can describe with confidence, and disappears behind an event horizon. It becomes a black hole. A stellar mass black hole is the ultimate endpoint of stellar evolution for the most massive stars. It is an object so dense that its gravitational field prevents anything, including light, from escaping once it crosses the event horizon. The interior of a black hole, according to general relativity, contains a singularity, a point of theoretically infinite density, where the known laws of physics break down. Whether this description is physically real or simply a sign that general relativity is incomplete at extreme scales remains one of the deepest unsolved questions in theoretical physics. Stellar mass black holes typically have masses between 3 and perhaps 50 or 60 solar masses, though gravitational wave observations by LIGO and Virgo have revealed black hole mergers involving objects at the higher end of this range, and even beyond. These black holes are invisible. By definition, they emit no light, no radiation, no signal. They can be detected only through their gravitational influence on surrounding matter. When a black hole exists in a binary system with a companion star, it can strip material from its partner, forming a superheated accretion disk that emits powerful X-rays detectable by space-based observatories. Several such systems have been identified in the Milky Way, providing strong observational evidence for the existence of stellar mass black holes. Whether a massive star leaves behind a neutron star or a black hole depends on a complex interplay of factors: the initial mass of the star, how much mass was lost through stellar winds during its lifetime, the details of the explosion mechanism, and the physics of matter at nuclear and supranuclear densities. The boundary between the two outcomes is not sharp, and it remains an active area of research. Some theoretical models suggest there may be a range of initial masses that produce neither a neutron star nor a black hole, but instead result in a complete disruption of the star with no remnant at all. Others suggest the existence of exotic objects at the boundary between neutron stars and black holes. The physics of core collapse remains one of the most challenging and actively studied problems in modern astrophysics. What is certain is that the death of a massive star, regardless of what it leaves behind, is an event of cosmic significance. It enriches the interstellar medium with heavy elements. It triggers the formation of new stars by compressing nearby molecular clouds. It produces compact remnant neutron stars and black holes that continue to influence their environments for billions of years. And it connects the smallest scales of nuclear physics to the largest scales of galactic evolution in a single, violent, transformative event. The death of a star, whether it ends as a fading white dwarf surrounded by the dissolving glow of a planetary nebula, or as a neutron star spinning in the wreckage of a supernova explosion, is never truly an ending. It is a transition. The material that once belonged to the star, the hydrogen it gathered from a molecular cloud, the helium it forged through billions of years of fusion, the carbon and oxygen created in its aging core, the heavier elements produced in its final moments, does not disappear. It returns to the interstellar medium. It rejoins the vast reservoir of gas and dust that fills the space between stars, and in doing so, it changes the composition of that reservoir in ways that shape the future of the entire galaxy. This process, the cycle of stellar birth, nuclear processing, and stellar death, followed by the return of enriched material to the cosmos, is one of the most fundamental in all of astrophysics. It is called chemical evolution, or sometimes galactic chemical enrichment, and it is the reason the universe today looks nothing like the universe that existed in its earliest epochs. In the first few 100 million years after the Big Bang, the universe contained almost exclusively hydrogen and helium, with trace amounts of lithium and virtually nothing else. There was no carbon, no oxygen, no silicon, no iron, no element heavier than lithium existed anywhere in the observable cosmos. The periodic table in those early epochs contained only 3 entries. Everything else had to be built, and the only factories capable of building it were stars. The first generation of stars, known as population 3 stars, formed from this pristine metal-free gas. Astronomers use the term metals to describe all elements heavier than helium, a convention that can be confusing but is deeply embedded in the field. Population 3 stars contain no metals whatsoever. They were composed entirely of hydrogen and helium, and theoretical models suggest they were, on average, far more massive than typical stars today, without heavier elements to help cool collapsing gas clouds efficiently. The fragmentation process that produces small stars was suppressed. The result was a first generation dominated by massive, hot, luminous stars that burned through their fuel rapidly and died young, many of them ending as supernovae within just a few million years of their formation. No population 3 star has ever been directly observed. Their lifetimes were too short for any to have survived to the present day, and they existed so early in cosmic history that observing them directly would require looking back more than 13 billion years to the very edge of what current telescopes can detect. But their existence is inferred from theoretical models and from the chemical signatures they left behind. When these first massive stars exploded, they scattered the first heavy elements into the surrounding gas. For the first time in the history of the universe, carbon existed, oxygen existed, iron existed. The periodic table had expanded. The gas enriched by these first supernovae formed the raw material for the second generation of stars. Population 2 stars. These stars contain small but measurable amounts of heavy elements inherited from the deaths of the first generation. Population 2 stars are old, but not as old as the first generation, and many of them still exist today. They are found primarily in the oldest regions of galaxies, in globular clusters, in the galactic halo, and in the central bulges of spiral galaxies. Their low metal content distinguishes them chemically from younger stars and provides a window into the conditions that prevailed in the early universe. As successive generations of stars lived and died, each generation inherited a slightly richer chemical inventory than the one before. Every supernova, every planetary nebula, every stellar wind added more heavy elements to the interstellar medium. The third, fourth, fifth, and subsequent generations of stars formed from gas that was progressively more enriched with metals. Over billions of years, the metal content of the galaxy increased steadily. Our Sun belongs to the latest chapter of this ongoing story. It is classified as a population I star, a relatively young, metal-rich star formed from gas that had been processed through many previous generations of stellar birth and death. The Sun contains approximately 2% heavy elements by mass, a small fraction in absolute terms, but enormously more than a population 2 star and infinitely more than a population 3 star. That 2% includes the carbon, oxygen, silicon, iron, and every other element heavier than helium that exists in the solar system. Every rocky planet, every asteroid, every grain of interstellar dust incorporated into our solar nebula owed its existence to the deaths of stars that came before. The Earth itself is a direct product of this chemical evolution. The iron that forms the planet's core was forged in the final burning stages of massive stars and scattered by supernovae. The silicon and oxygen that dominate the Earth's mantle and crust were produced through carbon and oxygen burning in stellar interiors. The calcium in limestone mountains, the sodium in ocean salt, the phosphorus in every molecule of DNA, all of these were manufactured inside stars and delivered to the interstellar medium through stellar death. Without billions of years of stellar recycling, the Earth could not exist. A planet requires heavy elements, and heavy elements require stars. The connection extends further. Life itself is built from stellar products. The four most abundant elements in the human body, hydrogen, oxygen, carbon, and nitrogen, include three that were produced entirely through stellar nucleosynthesis. Only hydrogen predates the stars, having been created in the first minutes after the Big Bang. Carbon was forged through the triple alpha process in the cores of red giants and asymptotic giant branch stars. Nitrogen was produced through the CNO cycle in the hydrogen-burning shells of intermediate and massive stars. Oxygen was created through helium capture onto carbon and through oxygen burning in massive stellar cores. These elements were scattered into space through planetary nebulae and supernovae, gathered into molecular clouds, incorporated into a protoplanetary disk, concentrated into a rocky planet, dissolved into oceans, and eventually assembled by biological processes into the molecules that carry genetic information, catalyze chemical reactions, and build cellular structures. The trace elements essential to biology tell the same story. Iron, critical to hemoglobin and oxygen transport in blood, was produced in the silicon-burning shells of massive stars and ejected in supernova explosions. Zinc, essential to hundreds of enzymatic processes, was forged through explosive nucleosynthesis. Iodine, necessary for thyroid function, was created through the slow neutron capture process in asymptotic giant branch stars. Copper, molybdenum, selenium, each one traceable to specific nuclear processes inside specific types of stars at specific stages of their evolution. The chemistry of life is, in the most literal sense, the chemistry of stellar death. This realization carries a kind of quiet profundity. The atoms in a human body are not merely old. They are ancient, beyond any ordinary understanding of the word. The hydrogen atoms in a glass of water are approximately 13.8 billion years old, formed in the first minutes after the Big Bang. The oxygen atoms bonded to them may be 5 or 6 billion years old, forged inside a star that lived and died before the sun was born. The carbon atoms in organic molecules may have passed through 2 or 3 stellar generations before finding their way into the molecular cloud that collapsed to form our solar system. We are not merely observers of the universe. We are participants in a chemical narrative that stretches back to the very beginning of time. The cycle has not stopped. It continues today, in every corner of the Milky Way and in every galaxy throughout the observable universe. Right now, molecular clouds are collapsing. Protostars are forming. Main sequence stars are burning. Red giants are shedding their envelopes. Supernovae are scattering heavy elements across thousands of light years. Neutron stars are spinning. White dwarfs are cooling. And somewhere, in a molecular cloud enriched by the deaths of countless previous stars, a new star is igniting for the first time, carrying within it the chemical legacy of every star that came before. The Milky Way alone is estimated to form roughly 1 to 3 new solar masses of stars per year. This rate has decreased significantly from the galaxy's peak star-forming era, which occurred roughly 10 billion years ago, but it continues steadily. Star-forming regions like the Orion Nebula, the Eagle Nebula, the Carina Nebula, and countless smaller nurseries scattered throughout the galactic disk are actively producing new stars at this moment. Some of these stars will be small red dwarfs that will burn for trillions of years. Others will be massive blue giants that will live for only a few million years before exploding and seeding the next generation. The distribution of stellar masses at birth, this initial mass function, appears to be remarkably consistent across different environments and different epochs, suggesting that the fundamental physics of star formation has not changed significantly over the history of the galaxy. Each new generation of stars is slightly richer in heavy elements than the last. Each new generation of planetary systems has access to a slightly more complex chemical inventory. The universe is, in a very real sense, growing more chemically sophisticated with every passing epoch. Elements that were vanishingly rare in the early universe, elements like gold and platinum, produced only in the most extreme astrophysical events, become incrementally more abundant with each cycle of stellar birth and death. The cosmos is slowly filling itself with complexity, building the chemical foundation for increasingly intricate structures, from dust grains to planets to organic molecules to, in at least one known case, life. Whether this progression is unique to our galaxy, or whether it represents a universal pattern replicated across billions of galaxies throughout the observable cosmos, remains one of the great open questions in modern science. What is certain is that the process depends entirely on stars. Without their birth, their nuclear furnaces, their patient transformation of simple elements into complex ones, and their eventual death and dispersal, the universe would remain a vast, dark ocean of hydrogen and helium, chemically simple, structurally barren, and empty of everything that makes the cosmos interesting. Stars are not merely objects in the sky. They are the engines of cosmic evolution. And their story, the story of how they are born, how they live, and how they die, is the story of how the universe became what it is today. There is a quietness that settles over the end of this story. Not because the universe has grown silent, it has not, but because the processes we have followed, from the cold darkness of molecular clouds to the violent brilliance of supernovae, eventually lead to a place where time itself becomes the dominant force. The births and deaths of individual stars are dramatic events when measured against human lifespans, but when viewed across the full expanse of cosmic time, they are part of a rhythm, a steady, patient pulse that has been beating since the first stars ignited in the young universe. And that will continue beating for ages almost beyond calculation. The universe is approximately 13.8 billion years old. In that time, entire generations of stars have been born, have lived, have died, and have returned their material to the cosmos. The heaviest elements in the periodic table have been assembled, atom by atom, through billions of years of nuclear processing inside stellar interiors, and through the violent extremes of supernova explosions and neutron star mergers. Galaxies have formed, evolved, collided, merged, and reformed. The chemical composition of the interstellar medium has grown steadily more complex with each passing epoch, and on at least one small rocky planet orbiting an ordinary yellow star in an unremarkable spiral arm of an average galaxy, the elements forged inside ancient stars assembled themselves into structures capable of looking back at the cosmos and asking how it all began. But 13.8 billion years, vast as it seems, is only the opening chapter of the universe's full story. The era we inhabit now, the era of active star formation, of luminous galaxies, of main sequence stars burning steadily across the night sky, is, in the grand cosmic timeline, still relatively early. The universe has an enormous future ahead of it, and the fate of stars within that future is both humbling and strangely beautiful. Star formation will not continue forever. The raw material from which new stars are made, the molecular hydrogen that fills the interstellar medium, is finite. Every time a star forms, it removes gas from the available reservoir. Some of that gas is returned when the star dies, through planetary nebulae, stellar winds, and supernova explosions. But the return is never complete. Some material is locked permanently inside white dwarfs, neutron stars, and black holes, removed from the cycle forever. And some gas is converted into energy, through nuclear fusion, transformed from matter into radiation that streams outward into the expanding universe and is never recovered. With each generation, the reservoir shrinks slightly. The rate of star formation across the universe has already declined significantly from its peak, which occurred roughly 10 billion years ago. The Milky Way today forms new stars at a rate far lower than it did during its youth. Astronomers estimate that active star formation throughout the universe will continue for, perhaps, another 100 trillion years, a number so large that writing it out in full would serve little purpose. 100 trillion years is roughly 10,000 times the current age of the universe. During this immense span, stars will continue to be born, to burn, and to die. But the rate will slow progressively. Molecular clouds will become scarcer. Star-forming regions will become fewer and more isolated. The galaxy will grow dimmer, populated increasingly by the small, cool, long-lived red dwarfs that consume their fuel with extraordinary patience, and by the cooling remnants of stars that died long ago. Eventually, the last star will form. It will almost certainly be a red dwarf, a small, dim object barely above the minimum mass required for sustained hydrogen fusion. It will burn its fuel with exquisite slowness, perhaps for trillions of years, a faint ember in an increasingly dark cosmos. And when it finally exhausts its hydrogen supply, it will contract, cool, and fade, joining the vast population of white dwarfs and brown dwarfs and stellar remnants that by then will constitute the majority of objects in the universe. After the last star dies, the universe will enter what some cosmologists have called the degenerate era, a period dominated by the cooling remnants of dead stars. White dwarfs will continue to radiate their residual thermal energy into space, growing cooler and dimmer over timescales of trillions upon trillions of years. Neutron stars will spin down, their rotational energy gradually dissipating. Black holes will persist, feeding on whatever stray matter drifts within their gravitational reach, but growing increasingly isolated as the expansion of the universe carries objects ever farther apart, over truly immense timescales so vast that even the word billions becomes inadequate. The white dwarfs will cool to the temperature of the cosmic microwave background radiation and become invisible. They will become black dwarfs, cold and dark, no longer emitting any detectable radiation. The universe will contain matter, but it will contain no light, no warmth, no nuclear fires burning anywhere. The era of stars, which began perhaps 200 million years after the Big Bang and lasted for roughly 100 trillion years, will be over. This future is not cause for sadness. It is simply the natural consequence of the same physical laws that gave rise to stars in the first place. The same gravity that collapsed molecular clouds into protostars will eventually exhaust the supply of collapsible material. The same nuclear physics that powered stellar cores for billions of years will eventually process the last available fuel. The same thermodynamics that allowed stars to shine will eventually claim the last residual heat from the last cooling remnant. The story of stars is, at its deepest level, the story of energy flowing from concentrated, ordered states to dispersed, disordered ones, the story of entropy, unfolding across time on the grandest possible scale. But that future is unimaginably distant. Right now, in this present moment of cosmic history, the universe is alive with stars. The Milky Way alone contains an estimated 200 to 400 billion of them. Some are ancient red dwarfs and white dwarfs that formed 10 or 12 billion years ago among the earliest stars in the galaxy's history. Some are young blue giants in the Orion Nebula that ignited only a few million years ago and will burn through their fuel before our sun has aged appreciably. And everywhere between these extremes, stars of every mass, every color, every stage of evolution are burning, evolving, and contributing to the ongoing chemical and structural development of the galaxy. Somewhere tonight, inside a dark molecular cloud that no optical telescope can penetrate, a dense core is quietly collapsing. Gravity is pulling gas and dust inward, slowly at first, then faster. A protostar is forming, hidden from view, detectable only in the faint infrared glow of its gravitational heating. In a few 100,000 years, the core temperature will reach 10 million degrees. Hydrogen will ignite, a new star will be born, and the cycle that has been repeating since the earliest epochs of the universe will begin again. Somewhere else, a red giant is shedding its outer layers into space, returning carbon and nitrogen and oxygen to the interstellar medium through a gentle stellar wind. The material drifts outward, cooling as it expands, forming a faint shell of enriched gas that will one day be incorporated into a new molecular cloud, a new protostar, perhaps a new planetary system. Somewhere else still, the iron core of a massive star has just exceeded the Chandrasekhar limit. In the next fraction of a second, the core will collapse, a shockwave will be born, and the star will be destroyed in a supernova explosion that will briefly outshine hundreds of billions of stars. The debris will carry gold and platinum and uranium elements forged in the final instants of the explosion into the surrounding galaxy, where they will drift for millions of years before becoming part of something new. These events are happening right now. They are happening continuously. They have been happening for nearly 14 billion years, and they will continue happening for trillions more. The birth and death of stars is not a historical event. It is a living process, the heartbeat of the cosmos, steady and patient, endlessly cycling matter and energy through the great furnaces of gravity and nuclear physics, and every element produced, every atom scattered, every photon released contributes to the ongoing story of the universe, a story that began with almost nothing and has been building complexity, structure, and possibility ever since. The calcium in the mountains was forged inside a star. The iron at the center of the Earth was scattered by a supernova. The oxygen in every breath was produced through helium fusion in the core of a red giant that died before our solar system existed. We are surrounded by stellar legacy. We are made of stellar legacy. The night sky, viewed from a dark and quiet place, is filled with these stories. Every point of light is a star at some stage of its journey, burning hydrogen on the main sequence, swelling into a red giant, collapsing toward its end, or shining as the faint remnant of something that once blazed with the light of a million suns. The sky is not a static picture. It is a vast, slow-motion documentary of stellar evolution, playing out across distances and timescales that the human eye cannot perceive, but that the human mind, guided by science, can begin to understand. And perhaps that is the most remarkable part of this story. Not the physics of fusion, or the violence of supernovae, or the unimaginable densities of neutron stars, but the simple fact that a species living on a small rocky planet around an ordinary star in a vast and ancient galaxy has been able to piece together the entire narrative. From the cold darkness of molecular clouds to the final cooling of white dwarfs, from the first generation of metal-free stars to the chemical enrichment of the modern universe. The story of how stars are born, how they live and how they die has been reconstructed through centuries of patient observation, careful reasoning, and extraordinary human curiosity. The stars do not know their own story, but we do, and in knowing it, we understand something profound about our own place in the cosmos, that we are not separate from the universe we observe. We are part of it. We are made from it. We are one of the ways the universe has found to know itself. The stars are still burning. The cycle continues, and the night sky, calm and patient and filled with ancient light, waits quietly for anyone willing to look up and listen.